Saturn's rings are the most iconic and visually stunning structure in our solar system, stretching up to about 280,000 kilometers across, yet averaging only around 10 to 30 meters thick in many regions. They appear eternal, bright, symmetrical, almost unreal, but spacecraft data reveal they are slowly disappearing. Observations from Cassini, which orbited Saturn from 2004 to 2017, confirmed a process known as ring rain, where charged water ice particles from the rings are pulled by Saturn's gravity and magnetic field into the planet's upper atmosphere. Measurements suggest that between roughly 4,000 and 40,000 kilograms of ring material fall into Saturn every second. At that rate, scientists estimate the main rings could vanish within about 100 to 300 million years, a brief lifespan compared to Saturn's 4.5 billion year age. The rings are composed mostly of water ice mixed with rocky debris, and their brightness suggests they may be relatively young, possibly formed less than 400 million years ago from a shattered moon or comet. Cassini's final orbits, diving between Saturn and its rings, provided direct gravitational measurements confirming their mass and ongoing loss. The process is not dramatic or explosive. It is gradual and relentless. Saturn's most breathtaking feature is not permanent. It is a temporary spectacle unfolding on cosmic timescales, and we happen to exist during the era when Saturn's rings are younger than we thought. For decades, scientists assumed Saturn's rings formed alongside the planet about 4.5 billion years ago, emerging from the same disk of gas and dust that built the outer solar system. However, data from Cassini, which orbited Saturn from 2004 to 2017, dramatically reshaped that view. During its final grand finale orbits in 2017, Cassini flew between Saturn and its rings, allowing scientists to measure the rings' mass through precise gravitational readings. The results showed the rings are less massive than previously believed, roughly 1.5 times 10 to the 19th kilograms, about 40% the mass of Saturn's moon Mimas. This lower mass, combined with the rings' unusually bright and relatively clean water ice composition, suggests they may be much younger than Saturn itself. If the rings were billions of years old, they would likely appear darker due to continuous contamination from micrometeorite impacts over vast time scales. Instead, their brightness indicates an age possibly between 100 and 400 million years, recent in cosmic terms, when dinosaurs still roamed Earth. These findings support the idea that Saturn's rings could have formed from the breakup of an icy moon or comet. Rather than being permanent fixtures, the rings may be temporary structures in planetary history, spectacular but fleeting on the scale of billions of years. Ring rain is real. One of the strongest pieces of evidence that Saturn's rings are slowly disappearing comes from a process known as ring rain. Saturn's immense gravity, combined with its powerful magnetic field, pulls tiny charged water ice particles from the rings down into the planet's upper atmosphere. Observations from Cassini, earlier data from Voyager 1, as well as ground-based telescope studies, detected clear signatures of water-derived material flowing along Saturn's magnetic field lines into its atmosphere. These particles interact with atmospheric gases, creating measurable chemical changes, including elevated levels of hydrogen and oxygen compounds. Estimates suggest that roughly 4,000 to 40,000 kilograms of ring material fall into Saturn every second. At that rate, scientists calculate that the main rings could lose enough mass to disappear within about 100 to 300 million years, a short lifespan compared to Saturn's 4.5 billion year age. This process is not theoretical. It is supported by direct measurements of atmospheric chemistry and plasma interactions. The rings are not static structures frozen in time. They are dynamic, evolving systems, actively shedding material. Every second, Saturn is slowly reclaiming the icy debris that makes it so visually spectacular, confirming that its rings are continuously and measurably losing mass. Cassini's final dive confirmed it. In 2017, during its dramatic grand finale, Cassini executed 22 daring orbits that carried it through the narrow gap, about 2,000 kilometers wide, between Saturn's cloud tops and the inner edge of its rings. These close passes allowed Cassini to make the most precise gravitational measurements ever taken of the ring system. By tracking subtle changes in the spacecraft's velocity using radio Doppler data, scientists calculated the ring's mass with far greater accuracy than before. The results showed the rings have a total mass of roughly 1.5 times 10 to the 19th kilograms, significantly lighter than many earlier estimates, and about 40% the mass of Saturn's moon Mimas. Lower mass implies less material to sustain the rings over billions of years, supporting the idea that they are relatively young and temporary. During these final orbits, Cassini's instruments also detected complex organic molecules, silicates, and water ice particles falling from the rings into Saturn's upper atmosphere, directly observing the ring rain process in action. This was not theoretical modeling or distant observation. It was in situ measurement collected during close orbital passes. Cassini's final mission phase transformed Saturn's rings from a visual wonder into a quantified, evolving system whose future disappearance is supported by direct, high-precision data. Micrometeorites are polluting the rings. Space around Saturn is not empty. It is filled with dust, micrometeorites, and debris left over from the formation of the solar system. These tiny particles constantly collide with Saturn's rings at high speeds, embedding darker rocky material into the primarily water ice structure of the rings. Over time, this steady bombardment acts like cosmic pollution, gradually darkening and contaminating the bright ice. If Saturn's rings had existed for the full 4.5 billion years of the solar system's history, scientists expect they would appear significantly darker due to billions of years of accumulated debris. Instead, the rings remain strikingly bright and reflective, composed of more than 90% water ice in many regions. This relatively clean composition strongly suggests a younger age, possibly between 100 and 400 million years, consistent with mass measurements from Cassini. At the same time, ongoing micrometeorite impacts continue to alter the ring's color, texture, and chemical makeup. The rings are not frozen in time. They are dynamic structures constantly shaped by collisions, gravitational interactions, and material loss. Their brightness is not just beautiful. It is a clue that Saturn's most iconic feature may be both younger and more temporary than once believed, slowly evolving under the steady influence of cosmic impacts. The rings are mostly ice. Saturn's rings are composed primarily of water ice, making up more than 90% of their material in many regions, with the remainder consisting of rocky debris and trace organic compounds. The particles range in size from microscopic ice grains to chunks several meters across, and in some cases blocks comparable to the size of houses. Despite their immense span, stretching up to about 280,000 kilometers from edge to edge, the rings are astonishingly thin, often only 10 to 30 meters thick. Ice, however, is fragile in the harsh environment of space. Constant exposure to solar ultraviolet radiation, energetic charged particles trapped in Saturn's powerful magnetic field, and steady micrometeorite bombardment gradually erode and chemically alter the ring particles. Collisions between particles also grind larger chunks into smaller fragments over time. Gravitational interactions with Saturn's many moons further disturb and redistribute ring material, sometimes shepherding particles into narrow bands and sometimes nudging them inward. Because the rings are dominated by relatively soft water ice rather than dense rock, they are more susceptible to fragmentation, sputtering, and inward migration. Combined with processes like ring rain, where charged particles spiral into Saturn's atmosphere, this ongoing erosion means the rings are not permanent structures, but evolving systems slowly reshaped by radiation, gravity, and time. Gravity is pulling them inward. Saturn's powerful gravitational field constantly interacts with ring particles. Over time, these interactions cause orbital decay, with some materials spiraling inward and eventually entering Saturn's atmosphere. Other particles may collide and fragment. Gravitational resonances with Saturn's moons also disturb the ring structure, creating gaps, waves, and narrow bands. The system is dynamic, not stable. The rings are in constant motion. Magnetic field interactions accelerate loss. Saturn's magnetic field plays a key role in the gradual disappearance of its rings. Ultraviolet radiation from the sun can charge ice particles, allowing them to interact with magnetic field lines. Once charged, some particles follow those magnetic paths straight into the planet's atmosphere. Observations from the Hubble Space Telescope detected ultraviolet emissions consistent with water raining into Saturn's upper atmosphere, providing further confirmation of ring rain driven by magnetic. Scientists estimate a time limit. Based on current ring rain rates and measured mass, some studies estimate that Saturn's rings could disappear within 100 million years. That sounds far away, but compared to Saturn's 4.5 billion year age, it is brief. This suggests we are observing Saturn during a relatively rare phase in its life. If intelligent observers had existed on Earth hundreds of millions of years ago, Saturn might have looked very different, possibly with faint rings or none at all. The rings may have formed from destruction. One leading theory suggests Saturn's rings formed when a moon or comet ventured too close and was torn apart by tidal forces, crossing what's called the Roche limit. The debris spread into orbit, forming the rings we see today. If this is true, Saturn's rings were born from destruction, and they may eventually disappear the same way, gradually reabsorbed by the planet that created them. We are living in a rare moment. The most astonishing fact may be this: humanity exists at a time when Saturn's rings are large, bright, and clearly visible. If they truly last only a few 100 million years, then we are witnessing a temporary phenomenon. Future civilizations, if they exist millions of years from now, may look up and see a ringless Saturn. The symbol of planetary beauty familiar from textbooks could eventually vanish. Saturn's rings look timeless, vast, symmetrical, and impossibly delicate, stretching up to 280,000 kilometers across while remaining astonishingly thin, often just 10 to 30 meters thick in many regions. But modern science reveals a different reality. Ice particles are continuously falling into Saturn's atmosphere through a process known as ring rain, measured by Cassini between 2004 and 2017. Data show that an estimated 4,000 to 40,000 kilograms of ring material per second are being pulled inward by gravity and guided along Saturn's magnetic field lines. During its 2017 grand finale orbits, Cassini flew through the gap between the planet and its rings, directly measuring their gravitational influence and determining a total mass of about 1.5 times 10 to the 19th kilograms, lighter than once believed and likely temporary on cosmic timescales. Micrometeorites continuously bombard the rings, slowly darkening and altering their composition. The evidence is not theoretical. It comes from in situ spacecraft measurements, Doppler tracking, plasma data, and atmospheric chemistry analysis. Saturn's most iconic feature may last only another 100 to 300 million years, brief compared to the planet's 4.5 billion year age. The most beautiful planet in our solar system may be gradually losing its crown. The universe does not remain static, and neither